Hello guys, the topic of my project is performance comparison of various channel coding schemes in MIMO OFDM. So the first thing is my abstract. Nowadays, the demand for wireless communication is in exponential increasing. So in order to meet our users' need, we need a new technology to support lots of users. So in this project, I will apply convolutional encoder with MMSE detector and ZF detector in my OFDM MIMO system. So what's the OFDM? OFDM will divide a big string into lots of substreams and transmit data using a parallel orthogonal subchannels. So in the graph, you can see that the first thing is modulation, and the second is to parallel converters. So it will be transmitted in parallel subchannels. So using the orthogonal method, we can minimize the subcarrier channel frequency spacing, and also we can achieve more subchannels on the same bandwidth. So this is a way to improve the spatial efficiency. And also we use IFFT to reduce our calculation time. And the fourth thing is to add CP. CP is the cyclic prefix. Cyclic prefix will provide a guard interval to eliminate intersimple interference from the previous simple. So it's a way to eliminate the interference between the symbols. And we get our channel, and we will demodulation if we want to get our original signals. So this is the basic model of the OFDM. And the second is the MIMO. MIMO is a multiple input and multiple output. So in this system, both the transmitting end and the receiving end has multiple antennas. So in this graph, there are lots of, so it's only a graph about 2 antennas, but there are lots of antennas. If you want to add, you can add antennas in there. And so the signals can be sent through multiple antennas at the transmitting end. And the receiving end will also have lots of signal to get. And in mathematical method, if we analyze in this way, so if I only use 1 transmitting antennas and I have n receiving antennas, so the transmitting signal will pass through n different paths because there are n receivers. So I assume that every feeding is in each path is independent. So the maximum diversity gain is n because of n receiver. And if I use m transmitting antennas and n receiving antennas, the diversity will become m multiplied with n. So it's a very large diversity if we use a lot of antennas in transmitting end and receiving end. So we combine the MIMO and the OFDM together and to get our MIMO OFDM system. Here's the graph. And I use the convolutional code. I can use this example because this example is a type of convolutional encoder. So the data is sent from the input to the register, and the average start value is n. So there I only have 2 bits, 1 bits. So they only have 0 or 1. There are 2 conditions. So in here, this example is equivalent to an XOR gate. So the calculation rule of this part is if the data is the same, the output is 0. If the data is not the same, the output is 1. So we can say from here that the register 3 records the data of the first 2 cycles, And the register 2 records the data from the previous cycles, and the register 1 records the current data. And using our calculation rule, we can get the output, and the output is for the convolution code. And we can say that since the output will be influenced by the state of different register, so it means this system has a memory property. And the next thing is our channel. I used relay fading channel, and the relay fading channel is a statistical model for the effect of a propagation environment on radio signal. And it assumes that the magnitude of a signal that has passed through such a transmission medium will vary randomly or fading. And it's a very good model for urban building with many buildings, because in a very large buildings block, there will be lots of reflections and refractions if the signal is passed through this block. And the signal can be considered as a relay distribution, because the definition of this part of relay distribution is that there's no direct signal from the transmitting part to the receiving part. So if there exists a direct transmission and direct signal, this will be regarded as a Rayleigh fading. So if we use this in a multiple building block, there's no direct translation, so it's a relay channel fading model. And also, relay channel fading model is very suitable for the presence of a large number of scattered radio propagation environments. And at the receiving end, a large number of independent random variables are received, and the central limit theorem can be applied to consider this signal response as a Gaussian process. And the next is the BPSK. So BPSK is the simplest modulation model among the PSK theories. P is phase shift. So the equation here, we can see that there only have one bit, so the conditions can be 2, because it's B, not a quarter, not a Q. So in here, if we substitute the n into the equation, we can get the phase of the model will be pi or 0. So the signal will be the phase of the signal will be inverse. It's 0 degree to 180 degree. So this will be these are inverse. So we can say from our coordinate map that these two signals can be presented in this way. So if we use QPSK, the coordinate map will become a circle which have 4 different points which distributed on the circle, because there are 2 bits, so the condition is 2 with power 2, it's 4 conditions. But here for the BPSK, it's only have 1 bit, so you have 2 conditions, because 1 power is 2 power 1 is 2 conditions. And BPSK is very simple and it's very good for the tolerance of the phase change. And the next thing is MMSE. I used MMSE detector in my paper, in my simulation. And there are 4 steps to calculate the MMSE. The step 1 is for the model. So the system model is R equals to the HS plus N. The H is the MIMO channel, and the R is a received signal, S is a signal, original signal, N is a noise. So the error data is the original, the true signal minus the estimate F, estimate signal, with the transmitted with as a coefficient in here, multiply with the received signal. So as to how to calculate MMSE, this is the definition. We want to get the minimum number of the error data. So our way is to do a derivation of the F. F is the estimated signal. To do estimation, so it's in mathematics. So in this way, we can get our estimated signal as F. So the next thing is zero forcing detector. I use the zero forcing detector. The thing is that we will use a linear processing and also the serial interference cancellation and also the decorrelation detection. And the linear processing is a partial decorrelation operation, and the SIC is performed according to the magnitude of the signal energy. And the decorrelation detection is used a mathematic description, like I explained this in the last slide. So the goal is to eliminate H, and H is a channel estimation. It's like the MIMO OFDM channels. And also for the interference deletion, we were according to the received power of each user signal, and only one user is detected at a time, and the user with a strong power is demodulated first, and then the reconstructed is subtracted from the total received signal. The strongest user interference and rebuilds and offsets the second strongest interference, and so on. So here's my simulation result. I can run this as a code. I run this first, so I can wait for the result. The next thing is I will explain this the result here. No, I can explain this. So from the graph, you can see that the data of the MMSE is much better than the data of the ZF detector. And in the data that we can see, if we want to get the BER in the 0.1, the lowest SNR of this graph is the MMSE without channel coding. And if we want to get a BER of 0.01, the lowest SNR is the, oh, here comes the result. If we want to get the SNR into a BER of the 0.01, the lowest SNR is the MMSE with channel coding. So we can see that for the difference of the same BER, the MMSE's SNR will be 2 dB lower than the ZF detector. So we can say that MMSE is much is better than the ZF detector. And also we can conclude that if we do not use a channel coding in a very low BER level, the SNR will be higher. So we need a channel coding to ensure we get a very low BER rate. And this is for the time. And the time compression here, we can see that if we do not use channel coding, it will only cost a little time. If we use channel coding, the time will be like a double time. And for the very small symbol, the time is much faster than the large symbols. It's very obviously. And also, the ZF is only a little higher calculation time than the MMSE. So in the end, I will say that MMSE is a little better than the ZF detector. So in my project, I think MMSE with the convolution encode will perform better than ZF detector with the convolution encode. Both of them are in the MIMO OFDM system environment. So this is the end of my project. Thank you.